Why the James Webb Space Telescope was built. For as long as humans have looked up at the night sky, we've been asking the same quiet questions. Where did all of this come from? How did the first stars ignite the darkness? And somewhere among all these distant lights, are we alone? By the early 21st century, we had already launched powerful space telescopes like Hubble. Hubble showed us galaxies, nebulae, and cosmic beauty beyond anything imagined before. But as breathtaking as those images were, scientists slowly realized something important. We were seeing the universe's present and recent past, but the deepest chapters of the story were still hidden. The earliest stars, the first galaxies, and the birthplaces of planets were wrapped in cosmic fog, invisible to Hubble's eyes. That's where the James Webb Space Telescope comes in. James Webb was not designed to replace Hubble. Instead, it was built to go further back in time, deeper into space, and closer to the origins of everything we know. If Hubble is like a powerful pair of glasses, Webb is more like night vision goggles for the universe. It sees a different kind of light, one that reveals what ordinary vision cannot. You see, the universe is expanding. As it expands, light from very distant objects gets stretched, shifting from visible light into infrared. By the time light from the first galaxies reaches us, it has been traveling for more than 13 billion years, stretched so much that it's completely invisible to the human eye. Hubble wasn't built to see that kind of light clearly. Webb was. This is why James Webb specializes in infrared vision. Infrared light allows it to peer through clouds of cosmic dust that block visible light, revealing stars being born, planets forming, and galaxies assembling themselves in the universe's earliest days. It's like lifting a thick curtain that has been hiding the backstage of creation. But Webb's mission goes even further than cosmic history. Another reason it was built is to study exoplanets, worlds orbiting stars beyond our solar system. Scientists wanted more than just confirmation that these planets exist. They wanted to know what they're made of. What gases fill their skies? Do they have clouds, weather, or even the chemical fingerprints of life? James Webb can analyze the faint starlight passing through an exoplanet's atmosphere and break it into a spectrum, like a cosmic barcode. From that, scientists can detect water vapor, carbon dioxide, methane, and other molecules that tell a deeper story about these distant worlds. Did you know that James Webb can detect temperature differences of just a few degrees on planets hundreds of light years away? That sensitivity is so precise it's like standing on Earth and feeling the warmth of a candle on the moon. Another reason Webb had to be built was scale. To see faint, ancient light, you need a massive mirror. Webb's primary mirror is over 6 meters wide, made of 18 hexagonal segments coated in gold. Gold isn't used for decoration. It reflects infrared light incredibly well. This mirror allows Webb to collect more light than any space telescope before it, making the invisible visible. Did you know that if Webb's mirror were placed next to Hubble's, it would collect over 6 times more light? That difference is what allows Webb to see galaxies that formed just a few hundred million years after the Big Bang. But building such a powerful telescope came with a challenge. Infrared observations require extreme cold. Any heat from the telescope itself would interfere with the faint signals from space. That's why James Webb carries a giant sunshield, about the size of a tennis court, which blocks heat from the sun, Earth, and Moon. On one side, it's hotter than boiling water. On the other, Webb operates in temperatures colder than -200 degrees Celsius. This delicate balance allows Webb to remain silent and still, listening to the universe without its own warmth getting in the way. Did you know that James Webb is so sensitive that if it were pointed at Earth, it could detect the heat from a bumblebee on the Moon? That level of precision was once pure science fiction. Ultimately, James Webb was built because humanity reached a point where asking questions was no longer enough. We needed better answers. We needed a tool capable of looking into the cosmic dawn, into stellar nurseries, and into the atmospheres of alien worlds. James Webb is not just a telescope. It's a time machine, a chemical analyzer, and a storyteller. It was built to help us understand how chaos turned into structure, how darkness gave way to light, and how planets like our own might form elsewhere in the universe. And as we'll soon discover, once Webb opened its eyes, the universe had far more to say than anyone expected. The first galaxies. Webb looks back in time. When James Webb first began sending data back to Earth, scientists were hopeful, cautiously optimistic. But almost immediately, something unexpected happened. The universe didn't look the way our models had predicted. Webb was designed to look back in time, to see the universe as it was billions of years ago. And what it found challenged some of our most comfortable assumptions. To understand why this matters, imagine the universe as a growing city. Right after the Big Bang, everything should have been small, scattered, and simple. Early galaxies were expected to be tiny, faint, and slow to form. Astronomers believed that large, well-structured galaxies took billions of years to assemble. But Webb saw something different. In regions of space where scientists expected cosmic infants, Webb found what looked more like cosmic teenagers. Massive galaxies, surprisingly bright, surprisingly organized, appearing far earlier than anyone anticipated. Some of these galaxies existed just 300 to 500 million years after the Big Bang. In cosmic terms, that's almost immediately after the universe was born. So how could such large galaxies form so quickly? That question sent ripples through the scientific community. It didn't mean our understanding of physics was wrong, but it did suggest that galaxy formation might be faster, more efficient, or more chaotic than we thought. The universe, it seems, didn't waste time. James Webb achieved this by detecting ancient infrared light that had traveled across expanding space for over 13 billion years. Each photon it captures is a messenger from the past, carrying information from an era no telescope had ever clearly seen before. Did you know that when Webb observes these early galaxies, it's not just taking pictures? It's measuring their distance, age, chemical makeup, and star formation rates all at once, turning faint smudges into detailed cosmic records. Another surprising discovery was how chemically mature some of these early galaxies appeared to be. Heavy elements like oxygen and carbon were already present. These elements are forged inside stars and spread by stellar explosions, which means multiple generations of stars must have lived and died very quickly. This suggests the early universe was an intense place. Stars formed fast, burned bright, and exploded, enriching their surroundings at a pace that defied expectations. Did you know that every atom of carbon in your body was created inside a star? Webb is now watching the earliest versions of that process unfold, billions of years before Earth even existed. Webb also revealed that early galaxies weren't always neat spirals or smooth ellipses. Many looked distorted, clumpy, and chaotic, like cosmic construction zones. Galaxies collided, merged, and reshaped themselves constantly. Gravity was the architect, but it worked with raw energy and little patience. This chaotic environment may explain why galaxies grew so fast. Frequent mergers could have accelerated their evolution, helping them reach sizes that previously seemed impossible so early in time. And then there's the light itself. Some galaxies observed by Webb shine far brighter than expected for their age. One explanation is that they contain extremely massive stars, far larger than most stars forming today. These giants would burn hotter and brighter, flooding young galaxies with light before ending their lives in powerful explosions. Did you know that some early stars may have been hundreds of times more massive than our Sun? Webb is helping scientists search for indirect evidence of these long-lost stellar giants. What James Webb has shown us so far is that the early universe was not a slow, gentle place. It was fast, dramatic, and wildly productive. Galaxies didn't patiently wait billions of years to become impressive. They rushed toward complexity almost from the beginning. This forces us to pause and reflect. If the universe could organize itself so quickly after the Big Bang, what else might we be underestimating? How many other cosmic processes are more efficient, more creative, than our theories suggest? As Webb continues to look deeper, it's not just filling in gaps in our cosmic timeline. It's rewriting entire chapters. And with every new observation, the universe feels less like a quiet mystery and more like a bold, unfolding story, one that began faster, brighter, and earlier than we ever imagined. And this is only the beginning. Stellar Nurseries: How Stars Are Born in Darkness. To understand the universe, you have to understand stars. Almost everything we see in space, from glowing galaxies to planets like our own, begins with their birth. But for a long time, the actual process of star formation remained frustratingly hidden. Stars are born inside thick clouds of gas and dust called nebulae. These regions are cold, dense, and dark. Visible light can't pass through them easily, which meant that even powerful telescopes like Hubble often saw only the glowing edges, not the story unfolding inside. It was like trying to understand how a house is built by looking only at its windows. James Webb changed that. Because Webb sees in infrared, it can look directly through these dusty clouds and reveal what's happening at their cores. And what it's showing us is both beautiful and unsettlingly complex. Inside these stellar nurseries, gravity slowly pulls gas together. As the cloud collapses, it begins to spin, heat up, and fragment. Eventually, dense pockets form, and at their centers, new stars ignite. But Webb shows us that this process is anything but simple. Stars don't form quietly or alone. They're born in crowded neighborhoods, influencing and disrupting one another from the very beginning. In some regions, Webb has captured newborn stars blasting powerful jets of material into space. These jets carve through surrounding gas like cosmic blowtorches, shaping the nebula around them. The environment becomes a mix of creation and destruction, where one star's birth can trigger or prevent another's. Did you know that our Sun was likely born in a similar crowded nursery, surrounded by thousands of sibling stars? Most of those siblings have long since drifted away, scattered across the galaxy. Webb's images reveal details never seen before. Filaments of gas twisting like smoke. Shock waves rippling through clouds. Tiny protostars, still gathering mass, glowing faintly in infrared light. Some are so young they haven't even started nuclear fusion yet. They're stars in the making, caught in their earliest moments. What's especially surprising is how chaotic these environments appear. For decades, scientists imagined star formation as a relatively orderly collapse. Webb shows that turbulence plays a major role. Gas clouds churn, collide, and fragment unpredictably, leading to a wide variety of star sizes and lifespans. Did you know that the mass a star is born with determines almost everything about its future, including how long it will live and how it will die? Webb is now helping scientists understand why some stars become gentle, long-lived suns while others explode as supernovae. James Webb has also revealed that star formation is deeply connected to chemistry. Within these clouds, complex molecules form on dust grains, including water ice and organic compounds. These molecules can later become part of planets, comets, and eventually living systems. In other words, the ingredients for life begin assembling long before planets exist. Did you know that Webb has detected water ice in some of the coldest regions of space, clinging to dust grains in star-forming clouds? That same water may one day end up on planets orbiting newly formed stars. There's a quiet, poetic truth here. Every star you see in the night sky began its life hidden, wrapped in darkness. Only after millions of years does it emerge, shining openly across space. James Webb allows us to witness that hidden phase, the universe's most private act of creation. And it invites reflection. If stars are born from chaos, shaped by invisible forces and turbulent environments, what does that say about the larger universe? About us? The atoms in your body were forged in stars that formed, lived, and died long before Earth existed. Webb is showing us where those stories begin. As we move forward, we'll see that star birth doesn't happen in isolation. Around many of these newborn stars, something else is taking shape. Flat disks of dust and gas begin to spin, collide, and clump together. These disks are the birthplaces of planets. And with James Webb watching, we are closer than ever to understanding how worlds, perhaps even worlds like our own, come into being. New worlds forming, Webb and the birth of planets. When a star is born, it rarely forms alone. Around many young stars, a wide, spinning disk of gas and dust takes shape. At first, this disk looks smooth and unremarkable. But over time, gravity, motion, and chance begin to sculpt it into something extraordinary. This is where planets are born. For decades, astronomers could only infer what these protoplanetary disks looked like. They were too small, too distant, and too obscured by dust to study in detail. James Webb has changed that, offering us the clearest view yet into the cradles of new worlds. Webb's infrared vision allows it to see the fine structures inside these disks. Gaps, rings, spirals, and clumps appear, suggesting that planets are already forming, sweeping up material as they orbit their young stars. These features aren't just beautiful. They are evidence of active construction, cosmic footprints left behind by unseen worlds. Imagine a calm pond disturbed by a fish swimming just beneath the surface. You can't see the fish, but the ripples reveal its presence. In the same way, Webb sees the ripples in these disks, revealing planets long before they fully form. Did you know that some of the gaps Webb observes are wider than the distance between the Sun and Neptune? These enormous clearings suggest planets far more massive than Earth are shaping their environments early on. One of Webb's most important contributions is its ability to study the chemistry of these disks. It can detect water vapor, carbon dioxide, methane, and complex organic molecules swirling around young stars. This chemistry determines what kinds of planets can form and whether they might one day support life. Water, in particular, has drawn intense interest. Webb has detected water in the inner regions of some disks, surprisingly close to where rocky planets are likely to form. This suggests that water may be common during planet formation, not a rare accident. Did you know that Earth's water may have come from icy material delivered during the early stages of planet formation? Webb is now watching similar processes happen around other stars, in real time. Webb has also revealed that not all planetary systems form like our own. Some disks show signs of violent interactions, where material is pulled apart or warped by nearby stars. Others appear calm and orderly, forming planets in neat, well-defined rings. The universe, it seems, is highly creative when it comes to building solar systems. This diversity forces us to rethink old assumptions. Our solar system may not be the standard model, but just one variation among countless possibilities. Some systems may form giant planets close to their stars. Others may never form rocky planets at all. Did you know that astronomers have already discovered planets drifting freely through space, untethered to any star? Webb is helping us understand how such lonely worlds might form. There's something deeply humbling about watching planets being born. These disks of dust and gas may look insignificant from a distance, but within them lie the raw materials for mountains, oceans, atmospheres, and perhaps life itself. James Webb allows us to witness the earliest moments of that transformation. It shows us that planets are not rare cosmic accidents, but natural outcomes of star formation, shaped by physics and time. As we continue, Webb's gaze moves beyond birthplaces. It begins to examine fully formed planets, not just as points of light, but as worlds with skies, temperatures, and chemistry. And in those distant atmospheres, we may find clues that answer one of humanity's oldest questions. Are we alone? Alien atmospheres, reading the skies of distant planets. For most of human history, planets beyond our solar system were purely imaginary. Even after we confirmed their existence, they remained little more than shadows, detected indirectly through subtle wobbles and dimming starlight. We knew they were there, but we knew almost nothing about what they were actually like. James Webb was built to change that. One of Webb's most powerful abilities is something called transmission spectroscopy. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching us. That light carries information, like a fingerprint, revealing the gases present in the planet's sky. For the first time, we're not just counting planets. We're studying worlds. Webb has already detected water vapor, carbon dioxide, carbon monoxide, and methane in the atmospheres of distant planets. These discoveries may sound technical, but they are profound. They tell us about temperatures, weather patterns, and chemical processes happening hundreds of light years away. Imagine standing far from a city at night and knowing what fuels its power plants just by analyzing the glow in the sky. That's the level of insight Webb provides. Did you know that Webb can detect clouds and hazes in alien atmospheres, even when those planets are smaller than Jupiter? These clouds can completely change how a planet looks and behaves, affecting temperature and climate. Some of the planets Webb studies are extreme. Hot Jupiters, gas giants orbiting incredibly close to their stars, experience temperatures hotter than molten lava. Webb has measured how heat moves around these planets, revealing fierce winds that redistribute energy from their blazing day sides to their cooler night sides. But Webb's true promise lies with smaller worlds. Rocky planets are much harder to study. Their atmospheres are thin, and their signals are faint. Yet Webb is beginning to push into this territory, examining super-Earths and mini-Neptunes, worlds unlike anything in our solar system. In some cases, Webb found atmospheres thick with hydrogen, suggesting planets more like scaled-down gas giants. In others, the data hinted at heavy clouds or hazes blocking deeper views, reminding us that nature rarely reveals everything at once. Did you know that a single atmospheric observation can take hours or even days of continuous telescope time? Webb must stare at the same star with incredible stability, capturing minuscule changes in light that reveal entire alien skies. Perhaps the most exciting aspect of all is the search for habitability. Webb is not directly looking for life, but it is searching for environments where life could exist. Water vapor, moderate temperatures, and certain chemical balances may indicate planets that are not too hostile, not too extreme. But there's an important pause here. Finding these ingredients does not mean life exists. It means the stage could be set. Webb helps us understand how common these stages are across the galaxy. Did you know that our Milky Way may contain more planets than stars? With hundreds of billions of stars, that's an almost unimaginable number of worlds. As Webb studies alien atmospheres, it quietly reframes our place in the universe. Earth is no longer the only world with complex chemistry and dynamic skies. It's one example in a vast collection. And yet, Earth remains special. For now. As we move forward, Webb's discoveries begin to challenge not just how planets form, but how life itself might arise. Some of the most intriguing results are not about what Webb found, but about what it didn't expect to find. And that's where the story takes another surprising turn. Surprising chemistry. What Webb found that no one expected. When scientists planned the James Webb Space Telescope, they had clear expectations. They knew what kinds of molecules should appear in young galaxies, star-forming regions, and planetary atmospheres. They had models, simulations, and decades of theory. Webb was built to test those ideas. What it's doing instead is complicating them. One of the biggest surprises from Webb has been the richness of chemistry appearing far earlier and in far stranger places than expected. In the early universe, scientists assumed chemical complexity would be limited. Heavy elements take time to form, forged inside stars and spread by explosions. Yet Webb is finding signs of advanced chemistry in galaxies that existed shockingly soon after the Big Bang. This suggests stars lived fast and died young, seeding their environments with elements at a rapid pace. The universe didn't wait patiently to become interesting. It rushed forward. In star-forming regions, Webb has detected molecules that were once thought too fragile to survive intense radiation. Complex carbon-based compounds appear embedded in icy dust grains, protected within cold, dark pockets of space. These are the same kinds of molecules that later become part of planets and, potentially, living systems. Did you know that Webb has identified organic molecules in regions where stars are actively forming, not after the chaos settles, but during it? This hints that the building blocks of life may form alongside stars, not as an afterthought. Webb has also uncovered unexpected chemistry in exoplanet atmospheres. Some planets show carbon dioxide in surprising amounts, while others lack methane where it was predicted to exist. These mismatches force scientists to rethink how atmospheres evolve under extreme conditions. In some hot planets, intense radiation appears to break apart molecules, reshaping atmospheric chemistry in ways models didn't fully anticipate. In cooler worlds, clouds and hazes may hide gases beneath them, masking their true composition. Did you know that even a thin layer of high-altitude haze can completely flatten an atmospheric signal, making a planet appear chemically empty? Webb is teaching us that absence of evidence is not evidence of absence. Another unexpected discovery comes from planetary disks. Webb has detected molecules like water, carbon monoxide, and even more complex compounds in regions previously thought too hostile or too warm. This suggests that chemistry is more resilient than we assumed, capable of surviving and adapting across a wide range of environments. These findings quietly change how we think about habitability. Life-friendly chemistry may not require perfect, calm conditions. It may emerge in turbulent, energetic settings, protected in microscopic niches. Did you know that many of the molecules Webb detects are also found in comets within our own solar system? This strengthens the idea that comets may act as chemical messengers, delivering essential ingredients to young planets. There's a deeper realization unfolding here. The universe appears eager to create complexity. Given energy, time, and basic ingredients, it doesn't settle for simplicity. It builds layers, interactions, and possibilities. James Webb is revealing that chemistry is not rare or fragile. It's widespread, adaptable, and deeply woven into cosmic evolution. And that leads us to a powerful question. If complex chemistry emerges so easily, so early, and in so many places, what does that imply about life itself? Is it a rare miracle, or a natural outcome waiting for the right conditions? As we move into the next phase, Webb's discoveries begin to blur the line between astronomy and biology. The telescope's gaze shifts from chemistry alone to something even more profound: the potential signatures of life. Searching for life, Webb and the quest for cosmic clues. For centuries, humans have wondered if we are alone in the universe. That question has driven explorers, philosophers, and scientists alike. With the James Webb Space Telescope, we are finally beginning to address it with real data, not just imagination. Webb's search for life focuses on subtle clues hidden in the atmospheres of distant planets. Certain molecules, water, oxygen, methane, carbon dioxide, can hint at processes that, on Earth, are connected to biology. When found together in the right balance, they become tantalizing signs that life could exist, or at least that the planet has conditions that might support it. One of the most fascinating discoveries so far is the detection of water vapor in the atmospheres of several exoplanets. Water, as we know, is essential for life on Earth. Its presence elsewhere suggests that the raw ingredients for life may not be rare. But Webb's sensitivity goes beyond merely finding water. It can detect subtle patterns in temperature and atmospheric circulation, revealing weather systems that could affect habitability. Did you know that Webb can identify the presence of clouds and haze on planets hundreds of light-years away, and even estimate how high or thick they are? These layers can drastically change a planet's climate and potential for life. Webb is also beginning to analyze smaller, rocky exoplanets, the type most likely to host life. These planets are faint, and their atmospheres are thin, making detection difficult. Yet Webb's infrared instruments are capable of capturing faint signals that may reveal chemical imbalances, hinting at biological or geological activity. Every spectrum, every tiny dip or rise in light, becomes a story about the planet's environment. Some planets show puzzling signs, molecules that shouldn't coexist without some active process reshaping them. On Earth, similar imbalances are maintained by life itself. While it's far too early to claim a discovery of extraterrestrial life, Webb is giving scientists the first detailed look at planets that could potentially harbor it. Did you know that James Webb can detect subtle temperature differences on exoplanets, mapping how heat moves across their surfaces? This tells us whether a planet has strong winds, heat circulation, or atmospheric currents, factors that can make a world more hospitable. And yet, for all its power, Webb reminds us of how vast the universe is. For every promising signal, there are thousands of distant planets waiting to be studied. The telescope's observations are just the opening chapter in a decades-long search, and each new finding raises more questions than it answers. But therein lies the beauty. The quest for life is not about instant answers. It's about exploration, discovery, and the slow unraveling of mysteries that have fascinated humanity for millennia. Webb shows us that the ingredients for life are not isolated or rare. They are woven into the fabric of the cosmos, appearing in places we might never have imagined. As we continue, we must reflect on a humbling thought. The universe is vast, ancient, and full of surprises. James Webb is giving us the first real glimpse into that grand design, revealing that life may not be a single, unique miracle, but perhaps a possibility waiting to unfold across countless worlds. And as the telescope peers deeper, the question becomes not just where life might exist, but how abundant it could be, and what that means for our understanding of our place in the cosmos. The unseen universe, Webb's glimpse beyond the visible. When we look at the night sky, we see stars, planets, and galaxies glowing in visible light. But what we see is only a tiny fraction of the universe. Most of it is hidden: dark matter, faint early galaxies, and cosmic structures that escape ordinary telescopes. James Webb was built to reveal what cannot be seen. By observing in infrared, Webb can penetrate dust clouds that obscure newborn stars, peer into regions of galaxy formation, and even detect light from the first moments after the Big Bang. It's a window into the universe's hidden layers, exposing structures and phenomena that were once invisible. One of Webb's most astonishing achievements is the observation of extremely distant galaxies, some so far away that their light has traveled over 13 billion years to reach us. These galaxies are not only ancient, they are clues to how the cosmos evolved, how matter coalesced into stars, and how the earliest cosmic chemistry unfolded. Did you know that Webb can see light that left its source before Earth even formed? When we look at these galaxies, We are seeing the universe's history written in photons, a story billions of years old. Webb has also revealed structures within galaxies that were once hidden, such as dense star clusters, swirling gas filaments, and signs of early galaxy collisions. These observations help scientists understand how galaxies grew, merged, and evolved over cosmic time. Even closer to home, Webb studies nebulae where stars and planets are actively forming. The telescope reveals the interplay of gravity, magnetic fields, and radiation, showing us that cosmic formation is a dynamic, ongoing process. What once appeared smooth or faint now reveals complexity, turbulence, and beauty beyond imagination. Did you know that infrared light allows Webb to detect objects that are cooler than stars, such as rogue planets drifting through space, or the faint glow of distant comets and asteroids? This opens entirely new possibilities for discovery. Perhaps the most profound realization is that the unseen universe is vast, complex, and full of surprises. The cosmos is not static. It is active, evolving, and filled with processes that we are only beginning to understand. Every observation from Webb teaches us humility, reminding us that what we don't see can be as significant, or even more so, than what we do. Through James Webb, we are not just expanding our vision. We are expanding our understanding of existence itself, learning that the universe is richer, stranger, and more intricate than we could have ever imagined. And as Webb continues to explore, it promises discoveries that may challenge everything we think we know about the cosmos. Looking forward, what Webb could reveal next? As we reflect on James Webb's first discoveries, one thing becomes clear: we have only scratched the surface. The telescope has already transformed our understanding of galaxies, stars, planets, and chemistry. Yet, what it has revealed so far feels like opening a single door in a mansion full of hidden rooms. Scientists are just beginning to analyze the vast troves of data Webb is sending back. Each image, each spectrum, each photon collected may hide new surprises, unexpected structures, unusual chemical compositions, or planets unlike anything we've imagined. The universe is vast, and Webb is our first detailed guide into its earliest, most hidden corners. In the coming years, Webb will focus on the faintest, most distant galaxies, tracing the universe's growth from its first flickers of light. It will study thousands of exoplanets, searching for chemical fingerprints that could suggest life. It will peer into nebulae where stars are forming, revealing the dynamics of creation in unprecedented detail. Every observation will help answer questions, and, inevitably, raise new ones. Did you know that Webb has the potential to discover planets in the habitable zones of nearby stars, worlds where liquid water could exist? These findings could fundamentally change how we think about the frequency of life in the galaxy. Perhaps most exciting is the sense of anticipation. When Webb was first launched, its capabilities were theoretical. Now, it is real, orbiting 1,000,000 miles from Earth, silently capturing light that traveled across billions of years. Each new dataset could overturn decades of assumptions, revealing mysteries we never knew to ask. James Webb reminds us of the power of curiosity and the importance of daring to build tools that extend our senses. It teaches us that the universe is both comprehensible and endlessly surprising, and that our journey of discovery has only just begun. Did you know that Webb's mission is expected to last at least a decade, meaning we could witness discoveries that will reshape astronomy well into the 2030s? The questions it raises today may define the science of tomorrow. As we look ahead, one thought remains humbling: every star, every galaxy, every potential world Webb observes is a piece of a vast cosmic puzzle. And with each new insight, we move closer to understanding not just the universe, but our own place within it. The story James Webb is telling is still unfolding, and it invites all of us to watch, wonder, and imagine what lies beyond.